That's embarrassing. I hit the wrong button in the first 2 minutes of the video. I was on vacation last week, so I got all confused, forgot how things worked. So we actually learned that with Pythagorean theorem, that's a terrible right angle. Let's get back to the beginning. Any right triangle, this is going to be longest. Every time. Like we learned that when we first learned about Pythagorean theorem a few lessons ago. I think that was last unit. So that's the longest side. So on this example, this one right here is going to be the longest side. Okay? Because it's the hypotenuse. The hypotenuse is the side that is across from the right angle. Okay, the hypotenuse is always the side across from the right angle. So it's going to be the longest side. So that will not be your quickest way. Okay, this side right here, which is what we have been calling our long leg, is actually the shortest distance. Like here, this is the long leg, right? And that's really my reasoning. Okay, we know the hypotenuse is the longest side. So the shortest distance will be the long leg, okay, or segment CJ. All right. Sorry, oh, yes, I am. I don't want to do that now. Hold on. If we look at this drawing right here, which is just this drawing without the triangle drawn in it, there are actually lots of different paths that I can get to line L, which is your shore, from point C. Okay, lots of different paths. And if I exaggerate this, you can obviously see that this one appears to be the shortest distance. Because it is, because it meets the shore at a right angle. Oop, sorry. Oh my gosh. I pushed a button on my pen. I don't know how to make it stop. There we go. Okay, so the shortest distance from a point to a line is a segment that meets the line, not meets, at a right angle. Okay? Okay, so let's move into our second task statement. Looking at these awesome drawings, like what do we see? What do we notice? What do we see? Let me change pen colors. I have, which looks like a radius, right? Here I have a line, right, that's tangent at point R. That means it touches the circle at point R and only at point R. And I have a segment that crosses the circle at Q and P. We call this a chord, right? I see this point S out here also. All right, so we know that the shortest distance from the center to the edge of the circle is a radius. Okay? These are all radii, right? It's going to get messy if I keep those there. I missed. These line segments are congruent. That should be at point R. I'm not doing a good job drawing my lines. Yeah. All right, let me look something up. Okay, just want to reiterate this known fact. We're gonna erase this. Okay, write this down in your notes. Tangent line is a line that intersects a circle at only one point. We're going to say that is point R. Right, so why is segment PQ not a tangent line? Well, because it intersects at 2 points, right? Why is ON not a tangent line? Okay, it does intersect at just 1 point, but it's inside the circle also. Okay, so it's not a tangent line. Sorry, another thing I could say is if I were to extend segment ON as a line, I want that for that to be red, it would actually intersect the circle at 2 points. Another reason that ON is not a tangent line. All right, so let's look at this task statement. It says, draw a radius in the circle. Okay, so go ahead and do this with me. Mark the point where the radius intersects the circle and label it A. Construct a line perpendicular to the radius that goes through point A. Label this N. This line will be N. Okay, we're not going to construct with our construction tools because we do know how to do that. This will be line N. A line has arrows on it. Line N intersects the circle in exactly 1 point, A. Why is it impossible for line N to intersect the circle in more than 1 point? Because that's how we drew it. Okay, that is perpendicular because that's how we drew it. Line N is tangent to the circle at point A because that's how we drew it. We're good. I'm going to see if our curriculum has the student section. I've got to move ahead. I was hoping that the student section had GeoGebra so we could play with it a little bit more, but it doesn't. Okay, so let's go right here and make sure. So theirs is drawn much nicer than mine, and one of the responses to part 3 was, suppose line N intersects the circle in another point, B, then a portion of line N would be inside the circle. So if I were to draw that, let's change colors. Okay, if I were to draw another radius, we'll call this A prime. If I were to draw a perpendicular line that intersected in 2 spots, say point B, it's no longer tangent. Tangent intersects the circle in just 1 spot. Okay, so that one doesn't work. All right, cool. So what kind of line then is N? It's a perpendicular line because that's how we drew it. Nope, it's a tangent line, sorry, because it just intersects at one place. Point A. Okay, that's what we're getting at. It's a tangent line that is also perpendicular to the radius. Okay, so any tangent line on the circle is going to be perpendicular to any radii on the circle. All right, that's your takeaway from this lesson. And here we see it. So this would be a radius at point in it. The radius is segment AB, and line L is tangent at point B. Okay, therefore, perpendicular at point B, which we see right here. So when I have a tangent line, which is line L, any radius in that circle will be a perpendicular line, okay? All right. All right, let's have some fun with this one. Okay, before we get into the task statement, let's talk about this. If I wanted to figure out the sum of interior angles inside of a quadrilateral, which is 4 sides, I would need to know some information, all right? So the sum of the angles are A plus B plus D plus F plus E plus C, all right? I put those in parentheses, and remember with addition, parentheses are no big deal. They just group, okay, with parentheses, they just group. See, I'm not looking at the camera anymore. So the cool thing that we've learned, or something cool that we've learned through our geometry class is this is a triangle. I just split that quadrilateral, like cut it into two triangles. All right, that's why I grouped those angles. All right, those are two triangles. Now, what is the sum of interior angles in a triangle? Okay, the sum of interior angles in a triangle are 180 degrees. So A plus B plus C is 180. So I've got A plus B plus C equals 180. Plus D plus F plus E. That also equals 180. So what's the sum of interior angles in a quadrilateral, four-sided? So if I add up all these angles inside this quadrilateral, they will add up to 360 degrees. It's kind of magic, but it's not magic. All right, so let's look at this. The image shows an angle whose rays are tangent to a circle. Mark the approximate points of tangency. Okay, right there and right there. Draw the two radii that intersect the points of tangency. Oh, almost. Let's try one more time. That's better. Label the measure of central angle that is formed as W. We do know that these are right though, don't we? Because a tangent, oh, I did it again. I pushed the button. There we go. The tangent with the radii, where a tangent meets a radii, is 90 degrees. We just proved that. What is the value of W plus Z? Okay, so that's angle W plus angle Z. Well, we know these are 90, so I can say that, W plus 90 plus 90 plus Z, because that's a quadrilateral, that's 360. So what is just W plus Z? Well, let's solve for it. W plus Z plus, I'm going to gather like terms. 90 plus 90 is 180. Okay, subtract 180 from both sides. So W plus Z equals 180. And that's not a mistake. Okay, that's another rule that you're going to want to write down because it works every time. Okay, W plus Z equals 180. All right, let's look at this. This is crazy, isn't it? All right, hold on a second. All right, on this last little activity, let's find as many right angles as we can. All right, I don't know if a highlighter is going to be easier here or not, but we'll try. So as many right angles. Remember, a radius plus a tangent. So like all the way from this segment to that one, and this one, because those are tangents and a tangent and a radius. Let's see. It's not, here's a radius, but I don't have a tangent to it. Well, this one right here, we learned that one right there, is 90 because it's an angle that touches the circle, and this is 180. Let's highlight that. This angle right here is 180 degrees. Therefore, this one is half of that, which is 90. Okay, we've learned that. What else? Ooh, let's change colors again. This angle right here is 90 because it comes out here and touches that line tangent to it. Okay. I don't see any others. Oh, here's another one. Change colors again. This angle right here is 90 for the same reason as that angle. Okay. I think that's it. Let's go check the answer key because that's fun. Let's see, ABC. Yep, we got ABC and ABD. Oops, I can't write on this. ABC is right here. I can't hear though. Okay, ABC and ABD are right here. These are going to disappear though, right? We know that CD is perpendicular. Yep, because CD is a tangent to the radius. Now angles BGF, yeah, that's this one right here, and BHF right here. Okay, we got those are each right angles because it's an inscribed angle. I didn't use the word inscribed, so I'm glad we looked. Whose associated central angle is the diameter, which is 180 degrees. The central angle measures 180, so the inscribed angle must be half of that, or 90. Okay, cool. We got them all. All right. Cool. That's it. Good job today.